Let's solve now problem 1, page 319 in Siegel's biochemical calculations. So problem number 1, and the page is 319. So this problem tells that the concentration velocity data shown below were obtained for an enzyme catalyze a reaction S to P, substrate to product. And the problem asks us to calculate Km and Vmax. Calculate Km and Vmax. So first let's approach this problem using software to get the solution. We enter the data that was provided to us directly into Prism, and now you analyze, and we want a non-linear regression. And we know that the curve is going to be a hyperbola, and with a click, we already get the result here. It comes in terms of Bmax and the Kd, which in our case it becomes Vmax and the Km, and we have the values there. Now let's transform this data to get the inverse, so that to do the way that normally we do in biochemistry. We're going to inverse both x and y. So we want an inverse of V and the inverse of the substrate. That's for generate the double reciprocal plot. So let's do that here, change now that we have the values already transformed. And then we're going to do a linear regression this time. And let's use everything as default. And another click in here. And we have the y-intercept, that's inverse of Vmax, as we know. So we change that and you get Vmax. And you have the y-intercept, which is the inverse of Km. So that we get then calculate the Km. So these are how the graphs look like. This is the hyperbola that we saw before in the first part. Fits in nicely. And we have the other graph, that's the double reciprocal plot, and get the same results. So that's how we will solve the problem. Now let's find an approximation for that problem. Okay, so we have the concentration of S and the velocity of the reaction given in nanomolar per minute. Let's pick up the first two ones, that's 2.5 10 to the power of negative 6. The velocity at that point is 24. The second one is 3.33 10 to the power of negative 6, and the velocity is 30. So in order for us to get the double reciprocal plot, we would have to do the inverse of S and get also the inverse of the velocity, instantaneous velocity. So for 2.5 10 to the power of negative 6 is going to be equal 400,000. And now we pick up the velocity, that's 24, and inverse this velocity, we are going to get 0.0417. Okay. For the other one, 3.33 exponential 60, change sign, invert that number, we get 300. And for the velocity is 30, we get the inverse of that is going to be 0.0333. All right. So this is merely an approximation, right? Because what we have here is that we have this this would be the inverse of the substrate concentration, and this would be the inverse of the velocity, right? So we know that we are going to get something like that nature, and we know that this is sloping here. This is, again, this is the y, this is going to be the x, right? So if you want to get this straight line here, first we have to know what's the slope. The slope of this thing here is going to be equal delta y over delta x, right? Then we can plug in, we have the equation ax plus b. So we can first calculate the slope and plug in here. So let's calculate that slope. The delta y, delta x. So let's say here, this all obviously 1 over s is going to be our x, and the 1 over v is equal our y, right? So let's calculate the difference in here. 400,000 minus 300,000, 300. So it gives us 99,700 for this one, and the 0.00417 minus 0.00333 gives us 0.0084. Okay, so we have our delta y and our delta x. So let's calculate that. What's going to be our slope? Our slope is going to be delta y, which is this value here, 0.0084, divided by delta x, which will be this value here, 99,700. Then if you divide that, we're going to get 0.084,9,700 equal 842 10 to the power of negative 8. Okay, so that's going to be the slope of this this line in here, this straight line here. That's going to be 8.42 10 to minus 8x plus b, right? Now you go on and we plug any of this. Again, I'm doing a very simple approximation so that you don't have to do all the work in an exam. So you can pick up any number here that we have for y, and any number that we have for x, and we replace it here to get the values that are missing, right? For example, we wanted to calculate first, we want to calculate how much is b. So let's pick up this value here. Let's pick up this one, that's y. It's going to be 0.0417 equal 8.42 10 to the power of negative 8 multiplied by this number, that 400,000 plus b. From that we can calculate how much is b, right? So 8 to 42 10 to the negative 8 times 400,000, and all this thing divided by 0.1417. So from here we get b equals 0.008. Okay, so that's the value of b, and we already know that the b is 1 over v max, because b is the number when x equals 0. That's the number that we get. That's b is going to be here, right? So we already know that b equals 1 over v max. Therefore, v max is going to be the inverse of 0.008. 2 zeros after they come and invert. It's going to give us 125. And which unit is going to be that? We are working here with nanomolar per minute, so this remains as such, nanomolar per minute. So we have the first solution here, that's the Vmax, right? So let me move this thing up a little bit here, get more space for us, and go back to find out the other value. So now the equation now is going to be y equals 8.42 10 to the power of negative 8 times x plus b, but b we already calculate what was 0.008, right? So with that I can plug in any number here and get what I want, right? So what's the value that I want in here is when x equals the number that we're going to get here when y equals 0, right? When y equals 0, then we get that number. That's an important number for us. So let's do that. Let's do it. Y equals 0. 8.42, 10 times minus 8 times x. That's what I want to find out, right? So it's going to be 84008 negative divided by 842 exponential 8 change sign. So what we get here is get that x in that case equals minus 95 250. Okay, so we know that number is km, right? That number is the inverse of km. So in order to us to calculate km, is going to be the inverse of this number here. That's x when y equals 0, right? So that's going to be km is going to be 1 over 95,250. So what you get here, get equals 10.5, 10 to the power of negative 6. This obviously is an approximation, and the km that we are working here, the concentration was in molar, so this would be in molar. We could say that approximately 10.5 micromolar, right? 10 to minus 6 molar. That would be the concentration, right? So that would be the solution for the first part of the problem. The problem goes on, and they ask you also to calculate the first order rate constant for the enzyme concentration employed. Okay, so move a little bit up here. Let's do now the part C of that problem. What we want to calculate here is the first rate constant. First rate constant. So because we are using here, so the first rate constant is when we have the substrate concentration much smaller than the concentration, than the Km, right? So in that case, when we have a situation like that, the V is going to be equal V max divided by Km times S. Michaelis-Menten equation here, right? Simplified for the situation when S is much smaller than Km. So we cancel that value there. Now, this ratio here would be the rate constant for the first order reaction, right? It's going to be K times S, right? First order reaction. So what we have then is that K, that we want to calculate, equals V max over Km. So how much was V max? V max was 125 nanomolar per minute. And Km was approximately 10 to, let's put it, to make it simple here, let's put it here, 10 to minus 5 molar. So let's, if we are going to do that to make it even easier to work, let's say 10 to minus 9 molar per minute divided by 10 to minus 5. Everything is approximation here, right? So that's going to be as K equals 10 to minus 4, 125. So that's going to give 1.25 10 to minus 2, and the unit is going to be, sorry, this was per minute, so that's going to be minute minus 1, or per minute. Okay, so that will be the solution for both parts of the problem.